Hello everyone, and welcome to this webinar offered by ERI and the Professional Development Committee. Our speaker today will be Professor John van der Lindt from Colorado State University, and we will have the pleasure of listening to his webinar, and then we'll have space for question answers at the end of the presentation. You have the chat the questions feature to ask questions that will be answered at the end of the presentation. Next slide. So here we have just some webinar protocols. You'll be muted by default, and we ask you to please keep your mic muted for the whole time. You should be able to have the computer audio activated by default, and the screen that you'll see is similar to that you see in this slide. As I said, you'll be able to submit questions and comments with the questions panel, and we will circulate a post-webinar survey afterwards that will be very happy to receive your feedback, comments on how to improve, some technical details about the webinar itself, and maybe think about future webinars. The presentation is recorded, and we are working with ERI staff to make it available in the coming weeks. So that's going to be probably available through ERI channels in a few weeks. Next slide. Probably you all know ERI, the Earthquake Engineering Research Institute, is a nonprofit membership organization with multidisciplinary professionals that is targeting advancement of earthquake resilience in the United States and globally. It's a global institution now. We have people from different backgrounds, and today's webinar is offered by the Professional Development Committee. The committee has been newly formed some months ago. I'm the co-chair with Professor Mervyn Kowalski from NC State. And we welcome, it's an open committee, we welcome new members of the committee. So please, if you feel you would like to join and work with us, let us know. Next slide. Today's speaker is Professor John van der Lindt from Colorado State University. I won't spend a lot of time about his bio. I'm assuming most of you know him very well. His presentation today is very interesting. I had the chance to kind of have a preview some days ago. It's going to be multidisciplinary. You'll see that there are a lot of insights on resilience, but also some interesting insights on social science and economics. So it is a webinar that's going to be really multidisciplinary, as it is John's background. So without further ado, I will leave the mic to Professor van der Lindt and welcome you to this webinar. Thank you.
All right, well, thank you very much, Paulo, and thanks to ERI for giving me this opportunity to share some thoughts on community resilience and the nature of how multidisciplinary it is. So with that, first I want to start with just outlining a few resilience efforts focused on natural hazards, and this is just limited to the US. If we went worldwide, it would be difficult to fit on one, let alone 10 slides, but there's efforts within the Department of Homeland Security, certainly the National Institute of Standards and Technology, which I'll be sharing a lot of that work with you today. The National Science Foundation, many of you out there listening may have done CRISP projects and other projects that focused on resilience, either at the regional or the community level, and then FEMA, the Federal Emergency Management Agency, with the BRIC program just recently released. HUD also is focusing on community and urban resilience. NOAA, EPA, as well as the Army Corps of Engineers, and then a lot of private entities, a lot of your consulting organizations and corporations out there, and member organizations, and then cities, counties, and states. I'm part of a group here at the state level in Colorado, focusing on revising or updating, I should say, the resilience plan for Colorado. So today's webinar, like Paulo mentioned, I'm going to start with some of the wood frame earthquake engineering examples, talking about structural failure, but as well as well-performing buildings, and then move into achieving seismic structural performance with cross-laminated timber, rocking wall project, things like that, and then move on to community and urban resilience. And in no particular order, I'm gonna jump around a little, and I hope by the end of the presentation you'll see why. But we'll look at some multidisciplinary test beds and field studies, computational platform that we're working on, which is very general, and hopefully people will be able to use very soon, and then implementation and partnerships and the need for that. So the stages of resilience, when we think of a lot of what we've done over the years in engineering research, it focuses a lot on stage 1 and stage 2. And that's looking at retrofits up in stage 1, and of course retrofits would allow us to get an increasing slope in that first stage, and then the immediate damage, essentially mitigating or reducing these. But resilience requires consideration of all 5 stages. That's the social and economic recoveries. Much at more of a community or a regional level, but much what the nation's going to be going through, over the next 2 to 5 years, most likely, but at a national level. And so in earthquake engineering, we're often focusing for many years, and it's certainly changed over the last decade, but for decades focusing on this first area to try and decrease the drop, the initial drop from the hazard or from the event, and then allow us to basically regain functionality quicker. So I want to start by going back. This project started more than 10 years ago, but I'll talk mostly about a test in 2013, and this was a series of tests. It was a large 5-university project with industry collaboration, and the goal. And many of you, if you're from the Bay Area, or even if you're not, you may recognize some of those buildings to the right, or at least the type of building. And these are these large, often rental units, but large soft story wood frame buildings, and they're really weak story buildings. And essentially a study showed that about a quarter of these would likely collapse in a magnitude 7.2 earthquake on the Hayward Fault. And so we collaborated on this NSF project to look at developing retrofit methodologies for this. And so I'm going to focus today on a 4-story full-scale wood frame test. But there was also some testing done at Buffalo, some large full-scale hybrid testing as well. So going to the world's largest outdoor shake table, or largest shake table in the US, located at UC San Diego. So we developed a building, or constructed a building, back in 2013. You can see it's ready for testing. I'll go into this a little more, but we had some cross-laminated timber rocking wall retrofit. And so each of these was on the order of about 7 to 10 days to run the experiment, and then pull the retrofit out and replace and conduct repairs, as well as the steel special moment frame. And then looking at performance-based seismic retrofit, which involved the steel moment frame plus wood structural panels, viscous damper devices supplied by or loaned to us by Taylor Devices, and then a collapse test, which I'll show you, and that's essentially a building that doesn't perform well, and that's what these buildings would look like in a major earthquake, and then of course recycling the building to the extent we can. So this was the team. I want to just give a shout out to the PIs on the project, as well as our industry collaborators. And then we had 5 undergraduates work on it, as well as 2 PhD students that were on site the entire time. And so this just shows some of the construction. And these are, as you can imagine, if you, those of you that have conducted these large tests, they're big undertakings, but the reward is definitely worth trying to find the budget. And so the building is complete, and here you can see we've got as close, with the extent of the shape table, which is 25 by 40 feet. We've reproduced these existing buildings to the extent that you can on that size platform. And so this is the building. The towers that you see there, they're only there to prevent it from falling that direction, but the shake is in the other direction. And interestingly, for this building, I only bring this up because it's the only full-scale shake table test that I've ever conducted where we needed to put in finished wood floors. And so you can see them here, and that was primarily because these buildings, were built so long ago, at least the building this is modeling, that they don't have any steel hardware or metal hardware. And so a lot of the stiffness in the floor diaphragm came from not just from the wood planks, but also from this architectural or finish overlay. So I'm going to start with what we tested last. That was the phase 5, and this is the collapse testing. And so this is essentially a building that would not be considered. It would not be considered to have performed well, obviously, with collapse, but even just the extent that it was damaged in the smaller event. And this is representative of what these buildings would look like without retrofit. So we removed 97% approximately of the instrumentation, leaving, if memory serves, about 15 to 20 sensors. And so if you look at the collapse motion, this is the spectral acceleration. And so I don't think you can see my mouse. If I'll draw you up to this top right, almost top right. And if we're looking, the period of this 4-story building without retrofits is actually close to 1 second. Now that's obviously for a 4-story building, you can see how soft that is, or understand how soft that is. And so we're over here, and at 1 second, and that's in window D. And so we were trying to select which ground motion to use to collapse the building, to observe the collapse and study the collapse. And so in looking at this, they all looked about the same at 1 second. And so then we moved to the spectral displacement. And so then looking at D again, what we see at MCE level, what we see at 1 second is they're about the same, but then we see them start to widen significantly. And so we selected superstition hills. And from my time working with a lot of researchers in Japan, one thing that I learned, they were the first to do a lot of collapse tests. One thing that I learned in Japan was that for wood buildings and for a lot of buildings, the acceleration doesn't collapse. It's, in our numerical models, the force collapses at sometimes, or at least it's a non-simulated collapse, but in reality, it's the displacement that collapses a lot of these buildings. So this is the shake. We've muted the sound just to avoid feedback for you, but so I'll try and narrate a little as we go. So this is the full-scale 4-story building. This is a 1.8 G spectral acceleration superstition hill shake. There's quite a bit of seismic mass added to get us up to design weight or design mass, and so there's steel plates and other things throughout the building, distributed as evenly as possible. And so you can see we're not quite collapsing, but this building would have to be demolished because that bottom is at a close to 17% drift down at the base there on that first soft story. Okay, so I like to say we did what all good structural engineering researchers would do. We shook it again because it didn't quite collapse. And so this is the same earthquake. And what you'll see is that it never can get back to equilibrium. It tries to push itself to your right, but it's just too far over. And so this is the same earthquake. And I want to bring your attention to, actually it's gone now, but what I'll do is I'll do this. I'm going to bring your attention to this camera right here. And so this is that camera looking into this was actually a finished room, but unfortunately it was a 10 a.m. Shake because we had some media there, and so we weren't able to get a good shot in there, but and we couldn't delay to try and resolve it. So, and so this is the camera, and this is and so that's what I was mentioning before. That's what we call our one of our sacrificial specimens. So this is the result. So the FEMA P807 methodology was a report that came out of an ATC project, and that approach, we tested several retrofits with that. So the approach, it doesn't specify what the retrofit should be. It just tells you what the performance should be and how to get it. And so we did that with these cross-laminated timber rocking walls. For those of you unfamiliar with it, it's almost like a plywood on steroids. These are just layers of dimensional lumber, and hence the name cross-laminated. So we lifted basically these wide flange up and then bolted directly into the joists at the second floor diaphragm, or the ceiling of the first floor diaphragm level, and got good performance. It's still not up to code, but it's much better than you would normally have. But what I want to focus on for the time being is what we would call a superior or a very a good performing building. And so this is a steel special moment frame plus wood structural panels, and this was done using an approach that stemmed from some of the early concrete work by Nigel Priestley, and then on by Andre Filiatro and Brian Foles, and then Wai Cheng Pang and colleagues as part of the Kneeswood Project, and that was applied to a building I'll show you in just a moment. But that essentially didn't take into account torsion, and so as part of this project, Bamani and colleagues worked on this and developed an approach that allowed us to consider torsion in that displacement-based design. And so this is the steel special moment frame being pre-assembled to bring into the building. This is the second story, and this is two intersecting walls. They were just walls. They're going to become intersecting shear walls shortly. This is installation of the continuous rod hold downs to control uplift. And that was part of the design as well. And here you see one installed, and you can see the toenail stud packs that were put in for compression. So this is looking up at the ceiling level, probably on that second floor. And then here you see the little clearer shot. And then this is back down on the first floor level. And so that wall you were seeing, and just above the moment frame, you can see the shear transfer done with self-tapping screws. Okay, so this is just a quick video of that, and to show you, now this is actually 100%, this is an MCE level Loma Prieta scaling. And so what you'll notice is it doesn't actually look like much because the building does so well. And so, but you can see a couple of higher modes in there, and that's not unexpected. We did expect, well, we did expect a little bit more of the first mode, but we did get a second, and I think there was even a peak of a third, if we want to call it that. So it's a short earthquake. It's only 20-some seconds, this portion of it anyway, and then some low period or long period motion. Okay, so I want to go back more than 11 years ago now. So this was before the project you just saw, and this is E-Defense in Miki, Japan. For those of you who aren't unfamiliar with it, this is the world's largest shake table. So to give you an idea, this building is 10 stories tall. It's about 120 feet tall, and this is a 6-story door to give you a sense of scale. And then the shake table is about 50 by 65 feet, and it's 3-dimensional or triaxial. So we tested a 6-story wood frame condominium there that was designed using a performance-based seismic design philosophy that was developed as part of this project. This was called the Kneeswood Project. And here you can see the just a quick snapshot. I'll run through a little bit, but first, this was it was essentially, you can think of it as really a Gen 1 performance-based design, in that we controlled the drift at each story, but then we also controlled rod elongation for the continuous rod hold downs, things like that. And so this building was designed to have a probability of non-exceedance of 80% for a 4% interstory drift for the MC level event. Now, the catch with a shake table test is you really, if you're doing an MCE level, at least with buildings that can be damaged, you really only get 1 or 2 shakes, and you really only get one with a pristine structure. So you have to choose wisely. I do, again, another call out or shout out to the team. These were the people on the ground. These are their affiliations when they were there. A few people have moved around, but this is where they were at and this is what we all looked like 11 years ago as well. Okay, so to start this off, we shipped 20 full-size 40-foot shipping containers out of 3 ports in the US and Canada with North American lumber, steel for the base, as well as hardware. And here you can see the steel going in. And so this base frame was designed by colleague Steve Pryor at Simpson Strong Tie, and this actually doubled, or it served as the lifting frame, so a space truss to lift this onto the shake table. But it was also then part of a different phase of testing as well. And so here, this is just construction going in. You can see the shake table at the top, some damper tests and other things going on. This is the bottom floor, the bottom wood floor, and this is our largest stud pack. So this is going to get 2 and 12 nailing on both sides. The sheathing going on here, and you can see that when we get to the cross-laminated timber example, I would say just keep in mind that in a way we were kind of getting there already with the size of these stud packs, and that's because of the drift requirements. And so it's this overturning that we're imposing on the building. And here we're up to 5 stories, getting fairly close. And this is the big test day. We've already done some smaller tests and recorded damage and things, and so we're about 4 weeks into shake table testing. And this is the crew that's going to do the damage inspection following the shake, and that did it on the last 2 days of testing over the course of that month. Okay, so this is the shake. This is 180% of the Canoga Park record, which takes us up to MCE at the building period of about 0.5 seconds. And back then we were scaling to a single period. So those of you that scale with ASC 7, we would have done it differently, but we didn't know that. And so it's a little bit long on the front end here, and that's primarily in the control room. There's a count done to do an instrumentation check. So they count down from 10, of course, in Japanese, and then there's a 10-second pause, and then the shake. So this is 180% of Canoga Park, and you can see, great performance. We're not, nothing questionable. Again, continuous rods. The whole thing is designed using this direct displacement design approach by Peng et al. And I'll jump to the next. So this is inside the top floor, and you can see this is down at the 10-meter platform. So this is about 33 feet out, looking down at people watching. And we had this was the media day with these big tests. We tend to do a media day just for whatever reason, I guess either PR or just because people want to see it. And so that was close to 2G accelerations. So fairly large accelerations up there, and that's because we're stiffening the structure, and that's something that's just those competing objectives of structural and controlling content and non-structural damage. And so, so this is some of the response. I would draw your attention to ST3 down at the bottom right in the middle here, seismic test 3. And so 1,825 kilonewtons of force and about 211 millimeters of displacement up at the roof level. So really, what we would say fairly good performance. And then we did get some torsion. So those of you, when we include that 5% accidental torsion in the ELF, equivalent lateral force procedure, there's a good reason for it, because this was designed to be perfectly symmetric, and we still saw torsion. There were a number of key takeaways, and there's reports and papers, as you're seeing, come across the bottom there, so I won't bore you with too much of that. But I'd say the biggest takeaway was that for the two-story tests led by Andre Filiatro at Buffalo back in 2006, with between 2 and 4% interstory drifts at the bottom story of the two-story building, we saw this type of damage that you can read to the right. But we still had about 3.1% interstory drift at story level 5, and we were really seeing almost no damage, just a little bit of diagonal cracking from openings, window openings, and things on the drywall, and some slight nail withdrawal. So in essence, that was a big takeaway, was changing the performance expectations based on drift for mid-rise wood frame buildings. And so the last mention of the wood structures, a project led by Shalane Pei at Colorado School of Mines that I'm participating on, and a number of people to the right are as well. And this was the narytallwood project. This was the planning project, and then in 2006 it was funded by the National Science Foundation. And as part of that project, in 2021, we're leading to the full-scale 10-story validation test at UC San Diego. And that'll be open to people that want to come see it. So if you're in the area or you can get in the area, certainly we'd love to have you in the audience for that. And that'll be, the construction will start in May of 2021. So the idea is that this is a structurally resilient system, or you can think of it as performance, really, to be perhaps more accurate. This was a two-story test that was conducted in 2017 there. So remember, we're shaking in the long direction of the table, short direction of the building, which is the why it looks a little bit strange like that. So I'm going to play this. Hopefully it won't cause any sound problems, because this does have sound, and I'm going to skip around because it's about a 10-minute video, but I just want to show you a little bit of the construction. And it generally rains each day we start, but then stops. I don't know why. So I'm going to jump a little just to show you the construction of these mass timber structures. Now we've got our post-tension rocking walls going in. And then mass plates to get us up to seismic weight or seismic design mass again. Okay, and so with that, hopefully the audio worked on that. But so with that, so this is a post-tension rocking wall system. This is just a two-story version of what we'll see in the 10-story, and of course the building will look a little bit less like a specimen and more like a building. And again, I've silenced the audio just so that because there's not too much feedback. You can see this USB working here as this rocks. And so this is essentially 280% Canoga Park, the same test that was run in back in 2009 in Japan for that large building, for the condominium. We ran it twice in a row, and essentially to show that there just is no damage, even running it twice. And then a close up on the rocking wall. Hopefully these are synced. They should be, but and here you can see it's lifting as it should. It's intended to rock. This is an extreme close up on the left. And really, after this whole test series of 14 earthquakes, ranging from DBE to even 120% of MCE, the extent of the damage to the seismic force resisting system was some little nicks and cracks. So just excellent performance, and we're confident that the 10-story will work. So this is what it's going to look like. And again, the idea is to minimize downtime. And to do that, we have something. This is just submitted work, but this is something we're calling time to functionality fragilities, and this enables ultimately will enable a designer to look at what probability of exceeding a certain time to functionality they're willing to risk in their design, or to what they're targeting, I guess you could say, maybe is a better way to say it. Okay, so I want to move on to community resilience. So if you think of, we think of resilience in 5 areas of community stability. We think of them in terms of population stability, which is measured, these are just examples of what you could use for a metric to keep track of this, but it would be the percent of people remaining in their homes after an event. Economic stability, which could be measured by household income, employment rate, it could be the gross city or domestic product. Social services stability, and this is the metrics, things like to quantify availability of healthcare, things like the patient to bed ratio or bed to patient ratio, as well as educational facilities, K-12 schools. And then physical services stability, and this is the percentage of buildings remaining functional that we just discussed. Metrics to quantify availability of utility and transportation services. And then governance stability, which are metrics to quantify things like police and fire protection and other essential services. And what you'll notice that buildings, having buildings functional, while it is interrelated or dependent or interdependent with these other areas of stability, it essentially it's one of the 5 areas keeping buildings functional. So to give you just a quick background on kind of where I come from a resilience standpoint, our Center for Risk-Based Community Resilience Planning, it's led here at Colorado State University with 13 additional institutions or universities with close collaboration with NIST, and it was renewed this last February, so we'll be working on some of these things for the next 5 years at a minimum. And so there's 3 major topics that we consider most critical for the advancement of community resilience, and that's the ability to accurately model the community and efficiently, for that matter, data science and field studies, and then decision support and user engagement. This is our team, and I won't mention everybody, but I'll just mention my co-directors, Bruce Ellingwood and Jeannie Cruz. So for modeling, there's a number of ways to do it, and I know a lot of people out there listening and that I talk to every day or every week have developed really amazing numerical models, and so INCORE is intended, the Interdependent Network Community Resilience Modeling Environment is intended to be a computational environment, and so and of course to do that we're trying models and developing models, and so. Of physical infrastructure, the economic health of a community, the social services within a community, and then all of this is kind of wrapped in information science, obviously, and that's the data component that you saw. And so to do this, we look at the damage and loss from natural hazards on communities, and then the multidisciplinary recovery with these integrated databases, looking at, for instance, schools and housing and business recovery. And then most important from a decision standpoint is looking at what alternative actions can enhance community resilience and inform planners and decision makers. And finally, the key to that is verification and validation of models, so they mean something. So there's really two types of models that are essentially possible. And one is a model that's self-contained in the analysis, and then the other is essentially importing a raster or importing the hazard. And this could be something like ADCIRC, which is advanced circulation model for overland flow, and this is what's used. It's likely being used right now to predict Hurricane Laura's inundation and things like that. And those are run as fast as they can on supercomputers right before events, as well as for planning. So in economic modeling and analysis, one of a very powerful tool is a computable general equilibrium model. We've had a close collaboration with a team of economists on working within our center, and that's to develop a spatial component to that. And the reason a spatial component is required is because if you think of an earthquake around a large area, with the civil engineering infrastructure systems, I guess for lack of a better term, the spatial nature of it has to be linked to the economic model, whereas often that's not the case. For instance, for something that didn't damage spatially, and so we provide a range of economic and fiscal impacts, and that's possible if you change a code or you change a design code or you invoke a certain policy. And this allows the prediction of losses in production and wages and local economic sector, things like that. And so the idea would be, a simple concept here. This is a county over in California, or a portion thereof, and buildings and other infrastructure models are then assigned across, as you see in step 2 here, assigned to all the infrastructure in a community. There's a hazard model. I'm showing a flood here, and then this all translates into the economics model. And so this is just perhaps the simplest way to then predict the effect of a flood on the economy. And so this model is by Harvey Tutler and colleagues, and this is a well-known type of model. This is and I just wanted to kind of highlight that within this model, the way this is characterized, if you think of our current situation with the pandemic, closing businesses essentially either closing what's called firms in the model, or modifying their output and or input, then propagates through the whole system, and that's how they do these predictions. In social science, the important considerations in community resilience are population and employee dislocation, housing restoration and recovery, business interruption and restoration as well. And then from a modeling perspective, it's critical to have a suite of tools. And of course, the data that comes in is census data, as well as data collected from field studies. So in some of the early work that we had the opportunity to conduct, we learned about the interactions from a virtual community. We named it Centerville, not realizing that there's actually somewhere between 20 and 30 Centervilles in the US, which we learned later, they're all over. And this was a simple community. So you can see like this would be, this would, for example, this would be middle income, high density housing. Happens that one of the fire stations is nearby, and so this was numerically modeled, all of this, and the idea was that it had an economy, it had a social structure, and then it had the physical infrastructure and topology, and the idea was to have a common community model where engineers, economists, and sociologists could work together and begin speaking the same language, to the extent that we actually developed a glossary to start to understand, what the other was saying and what the other was referring to. And so this had buildings, water network, electrical power network, and roadways. And here we see some of them. And it has a gas network as well as telecom now. We've modeled many real communities, of course, too, but that was how this started. And so these are those three major thrusts that I mentioned. And so, six important, I guess, foci, for lack of a better term, that need to take place to truly be able to model and understand and affect community resilience. And that's, having that numerical model, outreach and community engagement, understanding mitigation and recovery, and then, of course, verifying and validating, and then modeling some of the more complex systems. And here we see the ports and the schools, and then including interdependencies or at the least dependencies, and propagating uncertainty through the whole system because it's risk informed, or as I've started to call it, resilience informed decision making. So this is the structure of Encore, and I won't go through this for obvious reasons, but just to show you this, to set up the whole built environment model would be just this item 1A here on the left, and then the social systems would we have things like synthetic population allocation algorithms, and these are all available for anybody that wants to use them, especially just have to log in and have an account made, which is free. And so as well as the economic systems, and those get a little bit more complicated if there's any economics out there listening, economists listening. The CG models are fairly complex. And so then here you can see we'd predict damage to the infrastructure. These damage models would be, damage fragility functions. So we have to have them for flood, we have to have them for earthquake, we have to, and many of you have developed fragilities for earthquakes, and those, and so that's essentially the same thing. So the architecture, of course, everything's in the cloud now, and so we've got our Python-based Encore, the web services, the web tools, and then the lab itself. And so last really thing I'll mention, just if you're interested in this, I think we're posting this presentation, and certainly we can have our team discuss. So community engagement requires partner communities, and that's part of understanding community resilience, and that's really one of the social science components of this. And so so we'll be partnering with 6 communities over the next 5 years. To model community resilience, you also need a portfolio of mitigation and recovery policies and funding sources and things like that. And so you have to understand, what's possible, but from a cultural and a sociological perspective. But then you also have to understand what's possible from an economic perspective. And then one of the most challenging is understanding recovery over time, the longitudinal nature of recovery. And so we do this through a major field study and being led by Elena Sutley, but there's other ways to do it too if there's data that are available. But usually it's like a lab experiment. Sometimes the data is not documented the way it needs to be able to set up these models. Complex systems, the two that come to mind, intermodal transportation and social institutions, and this could be the schools and the hospitals. And then I mentioned interdependencies and uncertainty, and a big one is scalability and resolution that I neglected to mention. But while we can put every building in, every street, we can do that. But when the city gets big enough, when it's Los Angeles or San Francisco, then it becomes more and more of a challenge. So I want to jump to just some validation studies for a moment. One was hindcasting the Joplin Tornado. I'll jump into this for just a second here in a minute. And then the Lumberton, North Carolina field study that I mentioned. So the Joplin, Missouri tornado in 2011, some of you may remember it, it was a massive EF5 multiple vortex tornado, estimated wind speeds of 220 miles an hour sustained. It killed 161 people and injured almost 1,200. And it actually had the losses, the direct losses were on the order of a small hurricane. To give you an idea, not anymore really, but it used to be that hurricanes had 3 to 5 and 10 billion in losses. Thinking back to when I was young, the built environment, in this initial study was looking at just buildings and electrical power network. So to do this, you need your archetypes to be able to assign to the community, and that's coming back to that community model I mentioned. And so there weren't a lot of tornado fragilities out there, really none at the time some of this started. There were a few that had been developed back at the beginning of this work, and so eventually a suite of 19 were developed. Let me jump back, sorry. A suite of 19 archetypes that was felt to be the minimum set that could minimum suite of archetypes that could model a typical community, not a metro area. So jumping back to this kind of I guess you could say slightly a confusing diagram. Really, the hindcast looked at this part of the work to this stage, and then it looked at just some of the metrics within these 5 stability areas. So this gives you an idea of the modeling. This is on the left, the 19 archetypes color coded within Joplin. The social system modeling that you would have. This tells you what's owner, renter occupied, the population counts in these types of buildings. And then from the census data, of course, we can go all the way down to census block and then synthetically allocate and actually assign a family to a particular building. It doesn't mean that that family is in that building, that's who's in there. What it means is that they're somewhere in that census block, and then if we then scale back up, we can reproduce that. And then looking at 3 different retrofits, and we do the same thing for a lot of the earthquake engineering studies as well. So the hazard model, this is the tornado path you can see on the top left. And then we assign, these are for damage state 1, 2, 3, 4, and I'll jump through that kind of quick, but and these are just showing 5 different archetypes just as a simplification. Looking at electrical power networks, these are the 18 color-coded by 18 substations in Joplin. And again, this is done, I'll show an earthquake example here shortly, but similar approach. Tornadoes tend to severely damage this, as you can imagine, like all wind events. We'll see that, unfortunately, down south by Thursday morning, I think, down in Louisiana and Texas. And then the CG model, the economics model that I mentioned, predicting losses. And so up on the top right, you can see kind of the simplified version. We take the functionality of all the buildings and we aggregate into these economic sectors that are used in the CGE, apply the capital stock reduction to the CG model, and then we can get household changes in household income, domestic supply, and employment rate, amongst a lot of other things for that matter. And the social science, I think this is actually, I'll jump over this because I just described that process, but we actually, go through, and then when we get to here, this is that assignment of allocation to the housing units. When we get to this step, we then use a logistic regression that's been produced from data, being gathered over 10, 12 years now, maybe even 15, I think, by part of the team, starting about Hurricane Ike, I believe. And then building fragilities, go through and can actually combine that damage state with the population dislocation algorithm to determine whether or not a family unit or a household in each building dislocated due to the event. So this is in a Jupyter notebook for if there's any programmers out there. I'm sure there must be, but and these are all available online as part of this process. And okay, so while I have just a few more minutes, I want to talk about the Lumberton, North Carolina field study. So this is a longitudinal field study. WAVE, this is, it's essentially it's an approach that allows us, the same cases or buildings to be observed and also to be over time. And so we track changes, we track decisions that are made at the community level and the individual level, and we try and determine why those decisions are made as well. And the key is, recovery is not a single event; it's a process, and we're finding out that modeling recovery is a real process as well. And so, this wave one was shortly after Hurricane Matthew. I led wave one, and then the subsequent waves have been led by Elena Sutley at the University of Kansas, who's a member of our team. And there's our wave four has been delayed, as you can imagine, but we're hoping to do mail and phone surveys in place. And for any social scientists listening, the part of that is the delay in restructuring the IRB and things like that. So Hurricane Matthew, the goal, as I mentioned, was to investigate the initial damage, which is in a way kind of the engineering component of it. But then each of the teams had at least one social scientist, each of the inspection teams and survey teams who conducted the door-to-door questionnaires or surveys. There was one social scientist and one engineer at a minimum. And so we began to do our best to try and cross the disciplines over and learn from each other. And that was in the same reason. That's the way we do the models, and we felt that was critical for an understanding of the decisions the decisions people and communities make to establish community resilience and recover. And so we work closely within this, as well as the whole project, through that cooperative agreement with the National Institute of Standards and Technology, and in this study to document the community interdependencies through data collection as well. And so far we've looked at households for 3 years and businesses for 2 years. And I imagine something more will be added as time goes on. This is the team one. It takes a lot of people to go door to door, 572 homes, I believe, and some on the order of 300 businesses in wave two. And then there's a first report and a second coming out, and that is posted online at NIST if anyone's interested in reading those. Okay, so I want to move back to earthquake engineering to close the conversation. So thinking of physical and socioeconomic resilience modeling for informed or resilience-informed decision making, and so this is actually kind of a simplified block version of the Encore flow chart that you saw, or flow diagram. And so you can see we build our systems with our community description, and then we model it. We go into 3, which is our spatial hazard, which in this case is an attenuation function, and then physical damage and functionality analysis, going through determining what's functional, and then passing that to that economics and that social science component, and those modules or models to calculate direct and indirect impacts indirect impacts of the earthquake, and then looking at resilience metrics. So similar to the tornado example. And then again, this is shows you these are the test beds that I mentioned that we learned from. You heard a little bit about Joplin, and then a little bit about Centerville. We also modeled Galveston, Texas, which looked like it was about to take another direct strike, but then it will be a direct strike in the next day or two, luckily. And then Memphis, metropolitan statistical area, which is this example that I'm going to show you shortly. And so this just shows the structure of to do something like this requires a lot of IT, as you can imagine. And so I'll jump. This is the resilience assessment of the MMSA, as we call it. This is done in Encore. So Encore is just a tool for us now, although we're still developing it. There's about 300,000 buildings in here, and some of you may be familiar with this because this was part of the Mid-America Earthquake Center, just as part of Mavis development, and then on to Ergo, and so those data sets are available, which we use for the MMSA testbed. And so this is a little small here, but this first plot down below on the left shows the number of non-functional buildings. And so for the case analysis, just pay attention to case 1 on the extreme left of each plot. The cases don't matter for this discussion. They're just different building resolutions. But so that would be the highest resolution, every building being accurately modeled. And so what you can see is that we're getting 40,000 buildings with an M7.1 and virtually no buildings with an M5.9. And then when we move on, going through the economics and the social science model, what we wind up with is on this next one is the change in employment. So it goes, of course, it goes down, negative with the larger earthquake, and then the number of people dislocated goes up the other direction. And so that shows how we can get these physical and the socioeconomic metrics from the physical damage, and then we would then step through time during the recovery and see how that changes, which I've not touched on here. So to close, and again, I say in conclusion, but for now, because community resilience is just a fast-paced topic with thousands of people worldwide working at different levels, whether it's national, state level, regional is quite popular. The modeling is coarser. We work at the community level. I think there's an old expression, that disasters are local, and so we feel the most impact can be made at the community level from a planning point of view. So in conclusion, performance of buildings is a necessary but not a sufficient condition for community resilience. And I hope I showed that early on by showing the 5 community stability areas, and that's just one of them, or even part of one of them. And then population, economic, social services, and physical services. Those are 4 of the of the 5, these are the 4 areas of community stability. There's good progress, but a lot of work remains in governance stability. It's perhaps the hardest to model because it involves essentially people making decisions and not always based on optimization. And then modeling one-way dependencies, that may be sufficient for these first generation community level resilience models and analysis and decision making. Interdependencies, true interdependency modeling is from an academic perspective, it's definitely attractive, but it may not be necessary for these what we call Gen 1, I guess. And then modeling and field study data standards for community resilience, it's a critical need. In other words, what's the standardization of this data, and we're hoping to help work on that as well. So with that, I'll just acknowledge NIST for continuing the funding and continuing to fund the cooperative agreement, and then for NESOF, just a long list of colleagues out there that worked on this and collaborators. Kneeswood, the same. Again, the PIs, and then all the people that were able to contribute at reduced costs, even though we were in the middle of the start of the last recession. And then just a reminder that Encore and we'll soon have elastic cloud computing, so you can grab a seat at the table free if you'd like to try it. And with that, I'll just say thank you, and you can follow me on Twitter at Calm Resilience, and I'll give you updates on everything we do, as well as occasionally something that has nothing to do with it. So with that, thank you.
All right, thank you so much, John, for the presentation. I think that we are perfectly on time, so we do have time for questions, and there are several of them already in my panel. So I would ask you, John, if you could please answer them one by one. I'm going to read the first, which is none of the soft story programs currently underway in California, covering about 20,000 buildings, require continuous rod hold downs over the height of the building. Neither does FEMA P807 or IEBC Chapter A4. Did any of your tests involve retrofit of the first story only without continuous rods? And this is from David Bonovitz.
Oh, okay. Hey, David. Yeah, thanks, Paulo. Yeah, David, two of those studies, the CLT rocking walls, those were actually done using your weak story tool. And that was Sankey Park. That was going back and forth with your colleague, I think I recall. The weak story tool, excuse me. And I know you. I believe you had some input with David Marr and colleagues on that. But yeah, the short answer is yes, absolutely. It was that the CLT rocking walls were done using the weak story tool and sized, and then we matched the hysteresis to what was needed in the location as well to minimize the torsion. And then the steel special moment frame, that Simpson frame that you saw, I only showed the big one, but there was actually a much smaller one that was put in just on the first level. We did, as part of those P807 retrofits, so that was I think phase 1 and phase 3 of the 5 phases in NESOF. And in doing that, we did sheathe the underside of the floor diaphragm, and I think added a few straps and things like that. But it was all done in that first story. We never, double quotes, never went up to the second story at all.
Okay, we have many other questions. There's one about the shake table test in Japan. Were there any implications of lifting the structure above the shake table for the structure in Japan? This is from Muhammad Khalid Saifullah.
What was the verb there?
Were there any implications on, I think, the performance of the structure, of the fact that the structure was lifted above the shake table for the large shaking table facility in Japan? I guess
was the question that it was lifted to the shake table?
Yep.
Yeah, it's interesting. We often thought maybe the lift, it was stiff. I mean, when Steve Pryor had put that together, I mean, I think we had about a half. It was on the 60-foot dimension. We had about a half-inch of deflection in that space truss on the outside or the inside. Actually, so it was stiff. But at one point we did feel as they were lifting it up, there was about an inch of differential displacement when they lifted one side to kind of get things settled. And so there was a time when we did feel like maybe that it caused a little of the torsion, but there's no way to know because it doesn't show up. Unfortunately, it doesn't show up in the free vibration test where we can get the periods and things like that. Even if they are 3-dimensional, we can't see it.
And I think that there is a question that is kind of a follow-up, and it has to do with what you just said, which is there a plausible explanation for the torsion that was observed in the shake table test? This is from James Villa. I think that, you were mentioning that, but, are there any other insights?
Yeah, I think so. One of the things that we see, we don't see it quite as much. We even saw torsion in a uniaxial test in that 2-story building I showed you, and we had put in some rods that didn't affect the performance, but just tried to straighten it out. And I think what we it doesn't take much to induce torsion, and I think that's why we have that 5% accidental torsion, and then probably could be even higher actually, but other than it would cost a lot of money, I think, in the end. But one of the things we see is that when in a triaxial test, when you get, say, a movement down, and then you get something that tries to rotate it, so it's moving left, then it's suddenly moving forward, and so any little imbalance becomes a more significant imbalance, and so it doesn't take much, and so we try to spread out the seismic mass, but these were 4,400 pound, 2 metric ton plates, steel plates that we were putting in Japan. I think we had 128 of them or something, and to bring it up to seismic mass. And so in putting these in, you position them as best you can, but if you're off by a couple of feet, and it's a front, or something's off, and it's on the edge of the building, you'll definitely notice. So there could have been reasons, but I'd say the 5% accidental torsion, in my view, is quite reasonable to include at this point, from what I've seen.
Okay, great. And a couple of comments about all of the questions we're receiving. Yes, the John Paul Pinelli, this is where questions can be answered. I'm going to get to your questions in a moment. Thank you. We also need to thank a lot of European people who, I guess, stayed up late to attend the webinar. Thank you. And then we will be making the slides available in the upcoming weeks. You'll receive some additional information from the ERI staff about it. So, we've had, John, some questions about all of these, so I wanted to address them first. We do have more questions. One is, how was the performance with the rocking walls as retrofit? This is from Muhammad Khalid Saifullah.
So the question is, how would the performance? Yeah, so the rocking wall retrofit, if for the CLT on the at the bottom floor, it actually did quite well, but it achieved the P807 objectives. But of course, the thing to keep in mind, like I think David's question, or related to his question earlier, is that it's a bottom story only retrofit, and so you're never going to quite, you're still going to that story is still going to be soft. It's just not going to be as soft and weak. And so the idea for that, I think at the time, I think we brought it up to 50% of what would really be required. I think ultimately, and somebody can correct me, but I think ultimately the city of San Francisco went to 60%, if I remember right, or 60, maybe it was 60% MCE. But at the time we designed it, and we were already rolling on it, and then I think it got slightly modified, which was a good thing. But it performed, and it really took the torsion out. I mean, it was really impressive. We had, interestingly, there were 4 walls to remove the torsion and only 3 walls for the design of the strength, so strength and stiffness. So it shows you how significant torsion on those types of buildings with the open walls for garages are. Okay,
we have some, multidisciplinary questions, and I think the topic is very versatile. One of which is, were there engineering seismologists with these testing procedures who could have explained why you cannot scale earthquake records of one specific magnitude and presume it can physically morph correctly into another earthquake? I guess, yeah, it's kind of a complex question. I think the bottom line here is that, how, the scaling procedure was performed, and if there are any insights on these engineering seismology issues that may arise when you do that, when you perform these testing procedures and scale earthquake records.
So in general for us, like scaling a record, like if we think back to Japan, we had talked to colleagues at USGS, Nico Luco in particular, and and used what we believed to be state-of-the-art scaling for a shake table at the time, and that was to scale the strongest ground, the most intense direction, whether it was fault normal, fault parallel, to what we were trying for, and then we put that in the direction parallel to the control room, and you can imagine why. and then taking that same scale factor, and we apply the same scale factor to the other direction, the transverse direction, and then we don't scale the vertical motion. We use that as recorded, and so that was the approach that we used for that. By the time we got to San Diego for the 4-story testing, we used more of a FEMA P807, FEMA P695 scaling approach, and that was where I think most people are, at least the structural engineers, are familiar with that. And so those are the approaches. But from a seismologist perspective, we didn't have a seismologist on the team specifically. And a lot of times, one thing to remember with a shake table test is that it's really an input-output problem. You're getting the output for the input you put in, and so if the input is too large, which sometimes does happen because you've got a feedback loop, and it's usually acceleration feedback going. This feedback loop is trying to reproduce what it can, but it's but sometimes you get a spike at a higher frequency, and it, if it's high enough, it's not a problem. If it's not, then it might induce something. But for the most part, the people working at these big facilities do a great job matching the spectrum.
Okay. Still on earthquake inputs, there is a question by John Paul Pinelli, who congratulates you for the great presentation as usual. His understanding is that these are all scenario-based analysis. Can you do stochastic analysis like we do in insurance models, with sets of 50,000 hurricanes and define resilience metrics similar to the average annual loss, probable maximum loss, etc., applicable to resilience?
Yeah, so the short answer is yes. What I showed, of course, within Encore and things, and doing these types of analyses are scenario, but we do have, like, looking back, say, simplest example would be the tornado example. We have idealized tornado models, which are a series of of rectangles overlapping one another, and then based on data for 50,000 past tornadoes over the decades, there's a random angle that's fit to a distribution, and so we do that for the actual planning, the decision making procedures, and so we can do the same for earthquake. And the truth is, with 300,000 buildings, it doesn't take that long to run, because they're not running the dynamic analysis. It's just pulling from fragility curves, and so a lot of that can be done in parallel as well. So we do that, but the thing is, with community engagement, and I can't speak for all, but we're finding that a lot of the policy or the decision makers, they look at it as, okay, from with a hurricane approaching in the Gulf Coast right now, they would say, well, what would our community need to do if a Hurricane Katrina hit us, or if a Joplin tornado hit us, or if a Northridge hit right near City Hall? What would we do? And so that's how a lot of that thinking happens. From a scientific perspective, yeah, we absolutely do that, and so we're trying to, we're at the point where we're wanting to convolve that for a full risk or resilience analysis. Sorry, that was a little long-winded.
Okay. A few more questions. One from David Bonovitz. In the last slide about the Memphis study, what does case analysis mean? I think there were 6 cases.
Oh yeah. So okay. So yeah. So we probably should have cleaned that one up. But the case analysis, what that was actually showing is it was showing that was related to, again, the community engagement part. And so case one was where we assign the best fragility to each of the 300,000 buildings. And then as we went to case 2, 3, 4, 5, all the way to 6, it basically represents a community with a decreasing level or capacity to be able to assign fragilities. And so there's either less knowledge, excuse me, less knowledge about what the buildings have for seismic force resisting systems, or they just don't have the capacity to assign it, whether it's, being a smaller community and not having an engineer on staff, or the ability to hire a consultant. So that's more about what we call making Encore usable and useful for communities.
One question about site amplification. Did you consider ground conditions, site amplification factors? Some building design experiencing different effects because of the site-specific near-surface ground condition. And this is from Meredith Fyfie.
So we, was that in relation to the shape table studies, or we do, there is some, so we do have the ability to do that in Encore but it's that tier 2 type of model that I mentioned, where it's a finite element model of the ground, the rupture itself propagating through the soil types, and then can be imported in, but we still import the raster of peak intensities, and so the type of data that's used to pull from the fragilities is the same, but so we can do that in Encore. For the shape table sites, we generally we've not done a lot of near fault ground motions. To be honest, I've always wanted to do some of those, but I think we looked at it from the perspective of that input output. How do we enable this design philosophy or these approaches or this validation to work, in a way for the masses, for as many buildings out there as possible. And so it's really in a way, it feels like a supply and demand, but there's a lot of places where there are faults. So understood. So the short answer was no for that. Sorry, Paul.
One question about the Encore. So how did you construct the decision-making algorithm for Encore? Did you use a validated data, or you combine transportation, or did you combine the transportation, electricity, and building environment as an input for their interactions? And this is from Basil Hatton Akancel.
Yeah, so great question. So some of that is actually still in progress. We have basic decision algorithms, but some of that is actually and part of the problem with that, and I'm sure our colleague that asked the question knows this, but part of the issue is that for us, Encore is we want it completely open source, and so like the CGE model that I've been mentioning, that was programmed by our economists and several mathematicians that they contracted to develop the open source solver. And so we have the same issue with the decision modules, and that most of the solvers are commercial, at least that give the optimal solutions. And so right now we're in the process of doing the validation on the open source solvers to make sure that they converge, because like for all the researchers out there, there's nothing worse than running something and it's not converging, and your input's right. So right now, what we look at is, right now we're looking at an example, a flood example, to see, where to put levees, to do things like that. And so these are, but yeah, these are, there's really a suite of different algorithm types. I think that was more to the question. But some of that work is still in progress with some of our operational engineers on the team. We have 2.
Okay. 2 more questions on CLT systems. The first one is, are CLT rocking walls predicted to perform in high-rise buildings with more than 60 meters height? This is by Mina Fakeh. And there is another one on CLT system that I can probably ask later.
So I think 60 meters. I think we're looking right now. We're looking more at the 30-meter variety. I think going to 60 meters, is clearly the next step. And I think it'll require, a coupling of multiple walls to allow them, like you saw the two walls, those were, I think, 5 feet. So 1.4 meters each. And so, or maybe, yeah, I think they were only 5 feet. And so at 2 stories. And so the walls we have for the 10-story, the ratio, it's if you say it's 100, maybe 100 feet tall, they're about 2 10-foot walls, and then they're coupled with that same USP. And so you could, I think it would scale fine. I think the issue as we get taller would be, you have to get them connected into the diaphragms, and so you'd be spreading out, the connections. If you're using a CLT diaphragm, you'd be spreading that out, and so the diaphragms would, become 9-ply and become quite thick. But for a 60-meter building, that wouldn't be unusual. The problem is you would have that you would start to be using, maybe working against yourself from a sustainability perspective a little bit, in that your materials are getting larger and larger and larger. So there could be a price point, but I think it's, from an engineering standpoint, it's absolutely possible.
And then what do you think about post-tension, the rocking CLT system? Are they going to be a practical solution? What are the challenges you and the team identified so far as a seismic resistant design solution? This is from Selama with tires.
And was the first part of the question, Paulo, about putting it into practice?
Yes.
Yeah, so they're essentially ready to go in. We have, in fact, KPFF has been a close collaborator on the planning part, and they were developing designing the framework building along with others. That was supposed to go in in the Pacific Northwest. That was going to be an 8-story building that had some funding issues, so it wasn't a problem related to the engineering or anything like that. And so what turned out, it wasn't going to be built, but they're more like the technology is the technology itself is really ready for practice. And so Shileng Pei, who's the lead on that 10-story project, on the Tallwood project, has another project and with the U.S. Forest Service, and that's to write a best practices document for putting this into practice. That's, I think, halfway through. It's only a 2-year project, so that'll be about the same time we're doing it, and presumably that'll be one of the final documents to come out of this. So from a challenge standpoint, I would say the biggest challenge, the biggest challenge is, I think there's enough contractors out there that know how to do this type of work now, and so I think early on the challenge would have been, getting the mass timber contractors, because your average contractor, while they're their average construction crew, needs some training to be able to do it, but it's not that significant. It needs just being on a site probably for a few weeks to understand, understand tolerances and things like that, and read the drawings and things like that. So not a lot of challenges other than, and then a little bit on that force transfer to the diaphragm that I mentioned, and making sure that you're the modeling aspects, but that's more on the research side at this stage.
We have time for one more question, and it is by James Villa. How accurately do you know the drift in a shake table test? Is there some uncertainty, perhaps from being a double integration of acceleration? And the very rigid connection to the shake table seems very different from a real building embedded in a foundation in the ground. Does the shake table skew the performance from what actually happens in an earthquake? Is a complex question.
So 2 great questions. I'll just pass on them both. No, I'm just kidding. So with regard to the first question, it depends on the system, but for the big thing when conducting a model, running a model, is that the most important thing is to get the period correct, the fundamental period, the first, or if it's and then half the battle's won. So if you can, if your model, if you can predict the stiffness, the mass, of course, then it's just a matter of you're hoping to hit the peak. What we see often is that our periods are pretty close, and then sometimes we'll miss the big peak because a lot of our models are set up for the large motion. So when we do the smaller shakes, they don't always work as well, and so they're a little bit more sensitive, even though you're in the elastic, sometimes even in not quite the elastic region, but you're down there. So the short answer would be, I would say, I like to think we're within 20%, above or below for the peak responses. And if we can hit the period, we can maybe be in 10 or 15%. That would be my guesstimate. So the other question, that's something that we, all shake table tests and structural engineers that do, full scale and even scaled seismic research struggle with is we want to include, something, but we want to include something that for the soil structure interaction or things like that. The problem is that the soil boxes, while they help, they tend to not be large enough. And they tend to, at least the work that we've seen. And so while it would be great to do that, I don't think the shake table, the structural profession of research and shake table testing is, not really quite at the point where we can include it with confidence and sell it to the people writing the codes and working on those. And so I would say that there's a little, I think those two will connect at some point, but I think we're, probably a couple decades out from that. So I would definitely acknowledge that it's it's one of the flaws, but shake table testing is as close as we can come to reality for structures at this point.
Okay, John, thank you so much for everything. Just one last curiosity. I think we got a couple of questions on the same thing. Is there one document or a guidance document that can, be read to summarize this large subject? I guess you have a lot of references in your slides, but the question from people is there one document they can go to and kind of learn more about it?
It's an interesting question. I wasn't able to participate this year, but we were actually, I had put together colleagues from all around the world that have done full scale wood shake table tests out of Japan, US, Canada, and Europe as well. And we were going to, I think we had about 8 or 9 people, and we were going to, for the CEOG convention, we were going to prepare a paper that summarized all of those tests and talked about the needs, what's needed after that. It didn't happen, so that document's not available, so that doesn't help with the question. But but I would say there's generally a report on each, and then there are some documents. I guess I didn't catch our colleague's name, but if they want to email me, I can direct them to a couple of things, or I'm happy to provide ERI some information if they want to throw that on a site or something. But I would say there's probably about some of the challenges that it's we have like some of the work is published in Japanese by our colleagues over at Kyoto University, and then the majority of the work is in English, but some of these summaries would be in English, and so there's not one document, unfortunately, but there might be like maybe 4 that could get the point across.
All right. Well, yeah, I guess this is it would be great if that meeting will happen in the future. I think this is kind of a field of research where a lot of people can contribute from all around the world. So that'll be definitely something that we're all looking forward to. I think this was the last question. I would like to thank, on behalf of the Professional Development Committee of ERI, all of the attendees. You'll be receiving a couple of emails from the ERI staff in the next few days. And of course, I wanted to thank Professor John van der Lindt, who took the time to prepare and deliver these very nice presentation and answer to all of these questions. I think we've learned a lot, and this was definitely what we were looking forward to. So thank you so much, and have a good day.
All right. Thank you, everybody. And Paul, I think there was one slide after this, actually.